Okay, good. Thank you, Jose. Thank you, Matthew. It's an honor to be here. Thank you very much for joining us and for excusing me for speaking in English. I will warn you, I do speak a little bit fast, but I'm going to try my best. I've given a lot of lectures in French this semester, but I'm at the very end of a wonderful 6-month period here, and I'm just a little bit crushed to write out a lecture in French. I'm a much better lecturer in English anyway. Let me ask you a question, just because I don't know exactly who you are. How many of you have a background in social sciences? Okay, good. How many of you have a background in physical sciences? Okay, biological? Oh, good. Okay, well this should be fun. I'm a historian by training, but I wish I was a physicist, despite the self-confidence of all of my friends in physics. But I'm going to talk today about climate change and human history. And the talk has 3 parts. The first, which I'll try and get through fairly quickly, I think is probably the least interesting, but just talk about the history of climate and society, which is the subfield of historians who try to understand climate change and social dynamics. To talk a little bit more theoretically about the theme of today, tipping points and resilience. And because I'm a Roman historian, some of you are probably expecting a little bit of Roman history. I will provide a little bit of Roman history as a historical example, and I'm certainly happy to talk about it in more detail, but I don't plan to give a lecture on Roman history. And then finally, I will tell the entire history of humanity in 10 or 15 minutes to help us see some really big trends and to ask the hard question. I always prefer, as a speaker, to disappoint people at the beginning rather than wait to the end. So my argument is that the history of climate and society predicts that either future climate change will lead to collapse or it won't. I feel very strongly about that, but I'll try and at least say it in a principled way. So, and I left some of my slides in French because I worked hard to put them in French, so I thought, why work hard to put them back in English? The subfield of professional history, it's a small subfield, but one to which I more or less belong, known as the history of climate and society, tries to integrate data from paleoclimatology, the study of the past of the Earth system, domain knowledge from particular periods of history, in my case, for instance, the history of the Roman Empire, and then social science models, ways to think about the dynamics of human societies, and to bring all of those together. And this is, I think, a part of history that has a long, distinguished pedigree, but really is also at the same time something new. And it's largely new because of the influx of data from paleoclimatology. The urgency of anthropogenic warming has created a tremendous need to understand the Earth system and its past. And it's created a huge amount of funding, a huge amount of science in order to understand the past of the physical climate. So the need to understand things like the level of atmospheric carbon in deep time can only rely on instrumental observations going back, in this case, whatever it is, 50, 60 years, requires other kinds of proxy evidence to understand in deeper time the history of the Earth system. So how do you know how much carbon there was in the atmosphere thousands, tens of thousands, hundreds of thousands of years ago? You can't rely on instrumental observations. You need, in this case, ice cores that preserve datable traces of the past state and chemistry of the atmosphere. So this gives us a sense of climate change at different scales, including scales that are very interesting for historians. Here you see a reconstruction based on multiple different proxies, ice cores, tree rings, lake sediments, marine sediments, and so on, of the northern hemispheric climate reflected by temperature relative to late 20th century conditions since the year 1000. So this is 1,000 years of climate reconstruction for the northern hemisphere. And it gives you a sense of, this is relative to 1960, 1990, relatively stable climate. Living in the Holocene the last 11,700 years. Most of human history and all of the history of human civilization has taken place during a phase of the climate past, a geological epoch defined by really anomalous stability. And yet, here you can see anthropogenic warming, and yet this isn't completely stable. The Earth system varies and changes, and as a historian, we can take this new kind of information that we have about the past state of the climate system and ask interesting questions that we were unable to before about whether this impacts human societies. So over the last 20 years, there's been an explosion of scholarship that tries to address these questions. What can paleo-environmental data, paleoclimate proxies, tell us that we didn't know before about human history? And so over the last 20 years, I will also say that virtually every civilizational collapse has been climate change has been identified as a cause in every single crisis and collapse. Somebody even says the Roman Empire. But really, your collapse isn't even worth talking about if climate change didn't cause it. So we have all of this new data, and it suggests that climate plays a role. I'll argue that it plays a role. And we need this history. We need this history because anytime we think about risk, anytime we think about the future of climate change, we're doing history. Anytime you model the physical climate system, you're relying on knowledge that comes from experience of the physical climate system. The same is even more true if you're thinking about social impacts of climate change. If you're trying to measure the potential impacts of climate change, it involves history. So what this is, some of you may be very familiar with this. If you're not, very quickly, integrated assessment models are tools that are developed by economists. Bill Nordhaus is one of the first. He won a Nobel Prize for proposing an integrated environment economy model that tries to measure what are the trade-offs between climate change mitigation, so largely carbon regulation, which has a cost. Carbon energy is everywhere. You're wearing it, you're eating it, you're riding in it. So there are costs, but there are also benefits to mitigating climate change. And so economists, policymakers, the IPCC, the whole world thinks with these cost-benefit models. It's simply a cost-benefit model that says what are the trade-offs between different approaches to climate change. And to do that, you have to say, what's the cost of climate change? And to do that, these are always, if you really dig down underneath these always are based on historical data. They aren't just pulled out of thin air. And for the most part, it's based on historical data that goes back 20 or 30 years. That looks at things like GDP response correlation to small changes in temperature. So a huge amount of the way we think about climate change and the cost of climate change relies on this. There's a lot of work going on. This is sort of a summary of it if you're interested in where these models come from. It's simply an effort to find some kind of optimum policy choice that optimizes the relative benefits. There are huge amounts of uncertainties. I won't go too much into this. Here's a very good critique of integrated assessment models by the late Marty Weitzman, who put it well, it's deep-seated uncertainty on top of uncertainty on top of more uncertainty about the future growth rate of the economy, about the sensitivity of the climate system to carbon. We don't understand completely what's going to happen with the next emission of carbon into the atmosphere, and we certainly don't understand what is the cost to human societies of the next change in temperature. This is an extremely difficult problem. But I think it's one where historians can contribute to our understanding of the potential costs of climate change and simply the dynamics of the relationship between societies and the environment. Now, one of the reasons why this is an interesting field is because it helps us understand history. And so my motivation starts with the desire intrinsically to understand the human past, to understand what happened to past societies like the Roman society. But I also think that history can help us develop better science of risk and a better understanding of the complexity of human society and climate interactions. There's lots of attention, as many of you will know, to questions of tipping points in the physical climate system. That is, if we want to understand the sensitivity of the climate system to additional increments of carbon dioxide released into the atmosphere, this is a nonlinear relationship. We know this very well from history. There are a number of feedbacks in the system. For instance, the ice albedo feedback is a big one. If you have lots of white cover, reflects lots of heat back away from the Earth. If you melt lots of ice, you're trapping the heat, and it's going to be a positive feedback that accelerates either cooling or warming. And so there's lots of interest and attention in the last 10 years or so, particularly to these kinds of feedbacks that create critical tipping points in the climate system. But this is only really starting to influence the way that people think about human societies and social risk. And in fact, if you look at the sequential IPCC reports, it's just starting in the last couple of reports to work its way in to the way that social scientists are thinking about the impacts of climate change. And it is a really hard question. I probably won't belabor this, but climate and society are both extremely high-dimensional phenomena. When you say climate, and just thinking about the way that it impacts a human society, it's temperature, it's precipitation, it's seasonality, it's winds, it's clouds. What do you mean climate? You mean the average, the extreme, the duration, the variation, the interaction? And when you look at history, it can be very difficult to find really strong causal relationships for exactly this reason. So climate affects the agricultural system, but to understand the way that climate affects an agricultural system is already extraordinarily empirically difficult. Sometimes we know in history that entire societies would lose their harvest and starve with huge ramifications because it hailed for a few hours in July. That can be very difficult to model. It can be very difficult to understand dynamically. And so attribution is very, very hard in these kinds of cases. And here's from the IPCC. I love this because I think they just threw spaghetti on the ground. The causal structure of human-environment relationships is extremely complicated. Combine that with the fact that the further back in time you go, we're more uncertain about what was even happening. So our most precise climate records tend to be tree rings. They're really amazing records. Growth patterns in climate-sensitive trees are really extraordinary archives of the past climate. But imagine this like a thermometer reading. It's an instrumental reading that even if you understand it, it just tells you one number for a year. So there's a lot of uncertainty in this field. Nonetheless, I think we can make progress. Human societies are themselves complex adaptive systems. They're strongly affected by feedbacks, by stabilizing feedbacks, by destabilizing feedbacks that give us very good fundamental reason to believe that human societies we should imagine as complex systems. There's just now starting to be good, rigorous, quantitative, empirical models of this. This is a really good paper written by an ecologist and an archaeologist that's using this kind of model to look for bifurcation points in human systems that helps understand why sometimes human societies face climate change that's really severe and challenging and nothing happens. And so for some reason they're in a very stable condition where there's a strong basin of attraction towards stability. Then there's other times when human societies seem very fragile, that relatively little bit of climate perturbation, single difficult year, a single harvest failure can cause really significant climate outcomes. So that's a very good paper. I think one of the most unexplored areas in this domain is the way that climate seems extremely connected to activating and amplifying social phenomena that have positive feedbacks, not good feedbacks, but that tend to be phenomena like contagious phenomena. And so here is just a data set that's very interesting because it shows what you kind of probably intuitively know, which is that epidemic disease follows a power law distribution. You have lots and lots and lots of little epidemics, and then every now and then you get a Black Death. You get these huge, huge consequential events in human history. That is a signature of some kind of really strange dynamic that has to be, in this case we know is contagion, but probably conflict and maybe ecosystem collapse. I'm very interested to, this is a question that we'll learn more about shortly. But climate change has a very strong correlation with the frequency and the magnitude of the impacts of certain kinds of contagious phenomena like diseases, and I think potentially with war. So we can take this kind of thinking and use it to reconsider the past. I'm a historian of the Roman Empire. The Roman Empire is an empire that stretches across 3 continents, a really extraordinary system that includes an extraordinary diversity of ecology, all the way from the Sahara Desert to to the edges of Scotland, from the Atlantic, the entire Mediterranean. It's a huge, complex system. It's an agricultural society. So it's an economy that's very simple relative to ours. 80-90% of people live on the land. 80-90% of people work on the land. 80-90% of economic output is agricultural output. So it's very sensitive to climatic effects on agriculture, and this is primitive agriculture. So this is agriculture where, I love this mosaic because this is before the Green Revolution. Wheat is this tall. It takes 6 months to mature, and it has tiny little bit of seeds. So this is a really the agriculture of a very poor society. It's very vulnerable to climate change. And Roman history is very eventful. It undergoes phases of expansion and retraction. Roman historians love to debate about whether the Roman Empire falls or whether it doesn't fall, how many times it falls. I can tell you the answer is what I think. It's very obvious. It falls in the 3rd century, it falls in the 5th century, and it falls in the 7th century. I genuinely think that we should imagine the Roman Empire as a complex system that grows and then collapses actually multiple times. It is an empire that experiences relatively high degree of urbanization for a pre-industrial society, with maybe urbanization rates in the 15, maybe even 20% range, which is very high for a pre-industrial society, but it undergoes change. So here is a record of archaeological settlements from central Italy. This is one of the best records that we have, and we're going back 2,000 years. We don't have the kind of rich data that we have for contemporary societies, but this is from about 1000 BC to 1000 AD in the area around Rome. And you can see it's a story of change. There's growth, and then there are phases of collapse. And I'm going to look at 2 of these moments of contraction. In fact, it's the 2 proportionately largest moments when all of a sudden there's just a lot less people around the Roman Empire. And so historians love to debate this. I'd be happy to discuss it. But these are moments when seemingly there's some kind of population and economic collapse. What you're looking at here is a paper that we published a few months ago. It's a new paleoclimate record. All paleoclimate records are at best approximations with a lot of uncertainty. This one is based on a marine core off the south coast of Italy that uses little fossil single-celled organisms called dinoflagellates that some of the species are very environmentally sensitive and are used to proxy what's happening in the top of the water column in the Mediterranean just off of Italy. It's one source of understanding changes in the Holocene climate. And here you see the Roman history from the late Republic. So this is sort of when they sort of emerge over Carthage and are really the dominant power in the Mediterranean, right through the final collapse of the Roman Empire in the 6th century. And it provides both a precipitation record and a temperature record. And you can see it's a record of change. And what was interesting immediately to my collaborators and I when we were working on this is these moments when particularly there are rapid cooling episodes in the past, but also moments of aridity. And I'll say too, I won't go too much into this, that in many cases we have some understanding of the forcing mechanisms behind this kind of climate variation. The climate, the physical climate is always varying. And in particular, at these kinds of timescales, some of the really important mechanisms are volcanic forcing, so major volcanic eruptions that emit sulfur into the stratosphere that aerosolizes and hangs for a couple of years, can, but not always. The geoengineering people should maybe care a lot about this because it's very hard to understand why some massive volcanic eruptions have huge effects and some don't. Probably it involves ice albedo feedbacks, but in any case, there is a strong correlation between these episodes of cooling and relatively well understood volcanic eruptions, as I'll come back to, especially this one. You can see the climate people, not my friends in Roman history, are the ones who started calling this the Roman climate optimum. It's exceptionally stable. There is only one major volcanic eruption over this almost 350-year period. The solar radiation is very stable. This is the period when the Roman Empire is dominant. And then this is a period of turbulence and change. And again, this isn't completely arbitrary. I took a data set of 10,000 coin hoards, which others have also used as an index for trouble, economic trouble, or political trouble, or mass death. And you can sort of take this as sort of bad stuff is happening. You know, there's times when bad stuff happens, and in particular this episode totally stands out, right? History is not sort of a smooth, gradual, everything stays the same. It's that, and then these moments when things really dramatically change, cascade, and ultimately reorganize. In this case, there's harvest failure, there's barbarian invasion, which is, again, probably more than coincidence, right? The reason why there's conflict and invasion is probably because other people are starving as well. The monetary system ultimately breaks down, and the Roman Empire completely falls apart. For a time, right about here, there are actually 3 Roman empires, and there's no reason why it had to come back together again. It's just contingent that it happened that way. There's a mass death. I'm going to talk about pestilence more in a moment, but really everything goes wrong. And I think this is a sort of a lesson for us, because this is an example of a kind of compound collapse where multiple interdependent systems that can bear a lot of stress. The Romans, they have harvest failures all the time. They have invasions all the time. They have pestilence all the time. But when your money system breaks down, so if the dollar and the euro collapse, and if you have war, and if you have a pandemic, and if you have multiple people saying that the elections were rigged and I'm the real president, just imagine if that were to happen all at the same time, that a system can fail that was otherwise quite stable to perturbation. So I think the story of this is that this is coincident with the most severe moment of climate change in the record up to that point. And at this level of sort of coarse graining, it's very difficult to go beyond this kind of loose correlation. You can at least infer that there's a relationship between the climate stress and the social stress. Ultimately, the Roman Empire is put back together and enjoys several centuries more of history until the 6th century, which is, I think, the most consequential episode of climate-driven social crisis in the first millennium. In the middle of the 6th century, in the 530s, there's a climate anomaly that is actually so pronounced that numerous contemporary sources describe it. The sun disappears for a year and a half. People observe this, and the Roman historian Procopius says basically after this happened, nothing was the same. People tended to dismiss that, right? I mean, written ancient sources are superstitious. They say crazy things all the time. But actually, it was in the 1980s that 2 scientists at NASA first noticed that the observations of solar veiling in the 530s seemed to align with sulfate spikes in the Greenland ice core record. It was a really amazing intuition. It has since been absolutely validated and even enriched. We now know that in 536, there was a massive volcanic eruption in the northern hemisphere. 4 years later, in 540, there was a second tropical eruption that was even bigger. It was one of the biggest eruptions of the late Holocene. This is Somalis. This is the 536 and 540. This is the 1457 volcano. This is Tambora in 1815. There's something about the multiple volcanic eruptions right in a row that has some outsized effect on the climate system. And again, we don't really know why. I think a lot of people deep down suspect it's ice albedo. You just get enough years where there's the ice isn't melting, all of a sudden it's reflecting more heat. But what's now abundantly clear is that it is rapidly cooler. So these are two these are two tree ring records in red by Ulf Wünken, who's a strong advocate. We call this the late antique little ice age. You can see it's the coldest decade and the second coldest decade in these two records. This one is from the Altai Mountains. This is from the Alps in the late Holocene. So rapid climate change in the 6th century, probably the most rapid climate change of the last 2,000 years, on the order of a couple of degrees. I mean, 2 degrees is a lot. It's a lot of climate change. And there is a deep interest in understanding the ways in which the physical climate system affect human health, including through the mechanism of infectious disease. And this came out, that's late. This is an extremely complicated question. We understand pieces of it, but the climate system affects microbial pathogens and their physiology and evolution. It affects especially ecosystems and the hosts and the vectors that transmit infectious disease. And climate change affects human societies in ways that make them more or less vulnerable to infectious disease. So it can affect harvests that affect the population, health that can make a society vulnerable to epidemic outbreaks. In the 6th century, in this case, what's amazing is just 5 years after the sun disappears, the worst epidemic outbreak of the millennium happens. So you have the most extreme climate anomaly and the most extreme demographic anomaly that happen within 5 years. That obviously is not a coincidence, but we don't really mechanistically understand exactly how they're related. And part of the challenge is that the disease that shows up is a very complicated and particular disease. This may be weird, it's my favorite infectious disease. It's bubonic plague. I love it. It's a bacterial disease, still everywhere out there, but you're fine if you get it, just get some antibiotics going. It was discovered by Yersin in the mid 1890s. It's an animal disease. Most of our infectious diseases adapt to humans and become human diseases in the sense that humans can be the permanent host. So almost every major infectious disease that kills humans evolves to use the human being as a host. Not plague. Plague is really weird in that it is absolutely an animal disease. It's a zoonosis that can't circulate permanently in humans. It can for a little bit, but it always goes back to its wild rodent hosts, which are usually marmots or gerbils. It's also a vector-borne disease. Vector-borne diseases tend to be really nasty because they've figured out how to use mosquitoes, fleas in this case, to transmit from one host to the next. So plague is a really ecologically complex disease. It has to get from a wild rodent host, who in this case lives in Central Asia, to intermediate hosts like commensal rodents, black rats, and from there to humans. So the problem for understanding the climate relationship is that the climate affects every single link in that chain. It affects the physiology of the flea. It affects the way that the bacteria reproduce and the biofilm that they reproduce in the flea. It affects rodent populations. It affects human populations. We don't understand why the climate anomaly causes the plague outbreak. It may very well have something to do with the vectors, which seem quite sensitive, and certainly the flea bacteria physiology is affected by temperature. Plague is not only ecologically complex, it is also very complex in its pathology. It most often causes bubonic plagues, which is swelling of the lymph nodes, but it can get immediately into the bloodstream and cause septicemia. It almost always eventually gets into the bloodstream and kills you. It can also get into the lungs and spread via the respiratory route. So it's a unique disease. I won't read this whole thing, but when it arrives in the Roman world in the 540s, it is really the first Black Death. To me, it's unjust that the Black Death of the 14th century is so famous when this plague, the plague of Justinian, languishes in relative obscurity. It is a really extraordinary event that kills an extraordinary portion of the population. Most of our written evidence comes from the capital of the late Roman Empire, Constantinople, which describe in extraordinary, vivid terms the scope of mass death that this caused. So we don't have sound records like we do in modern times, where we can consult government mortality statistics. It's a very difficult problem to understand exactly how many people died, but we can say that it was a lot. I would say with confidence that it killed more people than any outbreak in the first millennium. It was really catastrophic. This is a really extraordinary moment of mass mortality. We're learning a huge amount about this now because we still need to study texts. This is a text, it's the most important text of the Plague of Justinian. It has never actually been studied. But we're also learning from new kinds of evidence, particularly ancient DNA. And I spend a lot of my time trying to find bodies that died of this thing. One of the real frontiers of knowledge, this is an amazing paper, I was not on this, but with a lab out of Jena that found plague in skeletons from this outbreak all over Western Europe, including in places like Edix Hill, which is a tiny little village in the absolute middle of nowhere. If the plague got there, it could have been anywhere. So we're learning a lot about this pandemic, but I think that it's a very important case study that shows us the ways in which climate change can be slow until it's not. And then when you get something about this double eruption that sets off a feedback that plunges the climate into this temporary cooling, that then sets off other ecological changes that affect human health. And again, there's a lot of interest in this right now. I think we'll know more in 5 or 10 years. But there's some link between the climate stress and this catastrophic mortality that really is an episode of catastrophe. And if you look at it over a decadal scale, is, I think, a collapse. So this is the Roman case. And of course, I'm interested and think a lot about, are we vulnerable to these kinds of social collapses? Is our society faced with anthropogenic climate change vulnerable to the kinds of extreme social collapse that the Romans experienced? And I often find that I really disappoint people when I say, maybe not. Some people really want me to say yes. But I think it's a very hard question. I want to spend the last, I've got about 10 minutes more, is that right? Okay. With my rapid view of human history that I think for me poses the hard question. Human history is a series of revolutions of a coupled system of metabolism and computation. So human history is a story of how one species acquires information about the environment that lets it control free energy in order to grow. And the story of humanity is a series of these really rapid revolutions, the control of fire, the control of sunlight through domestication of plants, and then the control of fossil sunlight. It's one of the things that makes us different from other organisms. Nature is very good at regulating the population of anything that needs energy. Chimps are really, really brilliant animals. There's never been more than a couple million of them because they run out of fruit and insects and things to eat. And so their populations are regulated because their information about the external environment is largely, not completely, limited to its DNA. Humans are weird. People are strange because of culture. It doesn't free us from any of the laws of nature. It doesn't free us from evolution. It's exactly as Maynard Smith said, it's a major evolutionary transition that we develop a new way of storing information about the environment that has relaxed many of the regulatory mechanisms that limit the population of every other living thing on Earth. When you think about human history, here's one way to look at it, the Roman Empire. And again, my Roman friends don't like it when I show this, but in some ways in the Roman Empire, nothing actually ever happens. The Roman Empire is not a place you would want to live. Everybody dies when they're like 20. No. Life expectancy at birth is in the mid-20s. Right? It's a world where there's no control of infectious disease. Life expectancy is short. Everybody is extremely poor. And after 8 centuries, they're as poor as they were at the beginning. The Romans, they don't really invent anything that interesting. I mean, they have a recipe for concrete. They're good civil engineers. But what, like, society-altering innovation did the Romans create? None. They invented nothing. This is a different world. Here is my chart that shows more of human history in one graphic. This is pre-industrial society. This is the 5 continents in 1820. Everyone is poor, and everyone dies young. So this is a log scale of income, and this is life expectancy. Everybody's poor and everybody dies young. This is the modern countries today, where even in the countries with the worst health outcomes, it's about twice as long as it was in the Roman Empire, and societies are much, much wealthier. The reason for this is economic growth. There are 2 fundamental sources of growth. The Romans don't enjoy any enduring growth. They have temporary growth because they have cities and trade, what we call Smithian growth. Adam Smith describes the benefits of people specializing in labor, exchanging their goods and ideas. But the main reason why the Roman economy doesn't grow, and modern economies do grow, is because of technical innovation. It's the root cause of growth is that we innovate technologies. This is rooted in ideas. It's a deep part of human history, and it particularly accelerates in Europe, somewhere in the 17th or 18th century. In Roman times, the Roman Empire is no ahead of any other major civilization. They're no more sophisticated or wealthy than contemporary Han China, than their rivals in the Parthian or Persian Empire. It's really not until somewhere in, economic historians debate this, the 16th or 17th century, that something starts happening in Western Europe. I think it does start in the 15th to 16th century. And here is a really powerful both reflection of that and explanation for it. You can see literacy rates in the Roman world are minimal. Nobody can read. Everybody is uneducated. There's 1% of the population can really functionally read and write. And that changes. And as that changes, people figure out how to get access to more energy. So the consumption of energy and the diversification of energy, including the use of fossil fuels, well predates the Industrial Revolution. Whenever you want to think of that as happening in the really late 18th, early 19th century, you can see coal. Already human societies in Western Europe, this is England, are finding new ways to get energy. And ultimately, the result of literacy, of science, is technical innovation. So I cite my favorite economic historian, Joel Mokyr. I've given it a little bit. He looks at England. I've tried to be a little more respectful of the home country here because it's happening in France as well. But the scientific revolution is the root cause of technical innovation and ultimately of social growth. It is the fundamental cause. If you look at what's going on in England, look at the patents of invention from the early 17th century. They're trying to figure out how do you get energy? How do you get coal? How do you hook coal to machine? They're getting any coal they can find. Of course, the English just stole all of the ideas, but that's another story. Ultimately, knowledge of the environment of the external world that accumulates in human culture leads to technical transformations that cause economic growth. So Newton, the rise of mechanics, has a very strong influence on the development of steam engines that revolutionize the economy in the late 18th and 19th century. And then really in many ways even more fundamental, although sometimes less appreciated in our thinking about history, is the second industrial revolution that's absolutely driven by improvements in particularly chemistry and then electromagnetism that lead to all of the transformational innovations that lie behind modern economies. At the same time, and not as a direct cause of economic growth, humans figure out, because of science, because of empiricist, self-correcting, knowledge-generating, cumulative science, they figure out how to control infectious diseases. In the Roman world, most people die most of the time of infectious diseases, but Europe figures out how to stop the plague. It's actually the most important disease. Europe figures out how to do it. Before they really have germ theory any kind of medicine that does any good. They figure out policies to stop the plague. And population grows. Ultimately, Edward Jenner is one of the great scientists of all time, absolute empiricist scientist, says we need to test this idea of exposing people to cowpox. Smallpox is the worst disease after plague. Europe controls the smallpox. Then you start to get some benefits of economic growth. People realize that you should clean water. People develop antibiotics quite late in the game. And then all of this in the 20th century, particularly in the context of decolonization, goes global. And so what happens when you stop regulating human populations by infectious disease and epidemic mortality? Population explodes. And yet, we may have passed peak child. It may slow down. But certainly, today, there are 8 billion humans on the planet who consume an extraordinary amount of natural resources. The flip side of this that I think about as a climate historian is that the kinds of phenomenon I study, I think empirically don't seem to operate over the last 2 centuries. So if you look at grain prices, first in Europe and increasingly globally, outside of extremely poor countries, the price of wheat is affected by the climate. But the level of variation that used to exist is simply gone. I mean, in the past, before the 17th, 18th century, the climate system could absolutely shut off food supply, right? That doesn't happen. It just doesn't happen in developed economies. It does not happen in the way that it happened in the Roman Empire. In the past, extreme climate events would cause extreme variation in mortality. And again, that does not happen. It just doesn't happen. This is the crude mortality rate since 1600, by which time England had already largely figured out the plague. If you go back a little bit further, the volatility was even more massive. So for hundreds of years in developed economies, we don't have pandemics like the Black Death or the Plague of Justinian. We just don't. We have not even, our parents, our grandparents, our great-grandparents have not seen a pestilence that killed a third of the population. It doesn't happen anymore. And the evidence here I think is much more mushy. But if you look at what happens with war, when you go back to the Roman Empire, you go back to the late Middle Ages, climate change stirs conflict. And this is something where there needs to be more work, but since about 1750, this is a Z-score for the relationship between climate and, it's a significant score for the relationship between climate, stress, and conflict. Used to be pretty visible that climate change played a role in causing societies to go to war. It just doesn't exist in modern times. World War II is not caused by conflict. By climate change. It's just not. I would argue that this is basically the right picture. And so the question is, have we escaped from these kinds of catastrophic effects of climate change? Another part of me worries significantly. If you know the literature on the causes of war, you know the work of Lewis Fry Richardson, physicists would like this, right? The impact of conflict is not normally distributed. It's not like height, where you have lots of people who are, 6 foot, and then you have a little bit of variation and very few outliers. Wars are, if wars were distributed, if heights were distributed like war, every now and then you would have a person who was as tall as the Eiffel Tower, right? It's a very different kind of phenomenon where every now and then you get huge conflicts that are orders of magnitude bigger, and these only happen every century or two. So the hard question is, have we escaped from these kinds of catastrophic impacts, or are we just preparing ourselves for the biggest one ever with CO2 emissions, with the acceleration of every measure of human impact and usage of resources, with energy consumption that shows no signs of slowing down, that could ultimately set off tipping points in the climate system that will then, of course, feed back on the social system. This is, I think, the hard question is whether, in a sense, because of technological growth, we are permanently more stable, or whether, in a sense, the Earth system is just preparing the biggest catastrophe of all time. But I think history shows us that when we think about the risks of climate change, we need to think about human societies as complex systems where there are powerful feedbacks. Our world is very different, and yet I think the biggest impacts of climate change could be felt through the intermediate mechanisms of economic depression, conflict, even pandemic disease, and hopefully we'll continue to learn more about the way that climate tipping points and social tipping points interact. Okay. Thank you.